At a red light, your phone's blue dot freezes in the intersection. But the bigger failure is not the map. It is the clock your phone was borrowing from space. So what breaks first if every satellite goes dark for one day? A one-day satellite blackout would not erase civilization. It would subtract precision from systems that were built to assume the sky could keep time. The first clue is inside GPS itself. A GPS receiver is not asking a satellite, "Where am I?" It is comparing timestamps. Each navigation satellite carries atomic clocks, and its radio message says, in effect, "I sent this at this exact moment from this orbit." Because radio waves move at the speed of light, an error of 1 microsecond is roughly a 300-meter distance error. The receiver needs signals from several satellites because it is solving four unknowns at once: latitude, longitude, altitude, and the receiver's own clock error. That same timing trick also sits under other global navigation satellite systems, including Galileo, GLONASS, and BeiDou. In the first minutes, the visible failure is ordinary. The map app leans on its last known position: cell towers, Wi-Fi clues, and motion sensors. The little dot may glide confidently for a while, then snap to the wrong street, then stop pretending. Cars do not shut off. Traffic lights do not all go black, but delivery routes, farm machines, survey tools, ride-hailing pickups, and emergency dispatch screens start losing the clean coordinates they were using as a shortcut. The first unresolved problem is transportation. If pilots and captains lose satellite navigation, do vehicles simply become blind? Not immediately, because aviation and maritime systems were not designed with only one sense. Airliners have inertial reference systems that measure motion from inside the aircraft. Pilots can still use radar, air traffic control instructions, instrument landing systems near runways, and ground-based radio aids where they exist. Ships still have radar, charts, compasses, coastal beacons in some regions, and humans watching the water. But GPS-dependent procedures begin to peel away. Some precise approach paths are unavailable. Oceanic aircraft tracking becomes less efficient. ADS-B reports, which often depend on satellite-derived aircraft position, may degrade even if ground radar still covers busy airspace. A single historical failure shows why this matters without turning it into doomsday. On May 1998, the Galaxy 4 communication satellite failed in orbit. It did not take down modern life, but it disrupted millions of pagers in North America and interrupted some broadcast and data services because many businesses had quietly routed a tiny but important part of their day through one spacecraft. That is the pattern, not instant collapse, but exposed dependency. By the first few hours, communication split into two worlds. Most internet traffic does not bounce through satellites. It runs through undersea and underground fiber optic cables, then through terrestrial networks. So a city apartment does not lose the internet just because the sky goes silent. But satellite television, satellite radio, remote broadband, aircraft and ship links, some rural backhaul, disaster zone terminals, and backup paths take direct hits. A remote clinic that used a satellite link has a very different day from an office sitting beside a fiber route. Then the second question appears. If people can still text in cities, why do forecasters start worrying? Because weather satellites are not just pretty cloud cameras. Geostationary satellites hover over the same region and provide continuous views of developing storms, smoke, fog, and lightning. Polar orbiting satellites sweep around Earth and collect temperature, moisture, cloud, and sea surface data, including measurements over oceans where there are few weather balloons or ground stations. Forecast models do not simply look out the window. They ingest observations in repeated data assimilation cycles. After 6 hours without fresh satellite data, the atmosphere over remote regions becomes less measured. Storms still exist on radar near land, but the early wide-angle warning picture is thinner. By late afternoon, the quiet failure is timing. Cell networks, data centers, financial systems, and electric grid monitors often use GPS or another GNSS signal as a reference to align clocks. The backup is called holdover. Local oscillators keep ticking after the outside reference disappears. Better clocks drift slowly, cheaper clocks drift more. That difference matters because some cellular systems divide time into tiny slots, so neighboring radios do not talk over each other. Power grid phasor measurement units use precise timestamps to compare voltage waves across long distances. Financial systems need ordered timestamps so trades and logs can be reconstructed. None of that means one missing satellite signal instantly breaks a bank or a power line. It means accuracy becomes a resource, and every system starts spending the quality of its local clock. The third question is what happens at the 24-hour mark, when backups have not failed dramatically, but the planet has become less synchronized. Airlines may add spacing and avoid certain routes. Ships and aircraft outside dense ground coverage may report with less precision. Weather models carry a data gap that can echo into later forecasts. Emergency managers lose fresh overhead images of floods, fires, or damaged roads. Remote communities feel cut off while fiber-connected cities feel only partial friction. If the satellites return, receivers and networks still need to reacquire signals, verify timing, and reconcile logs, so the recovery is not one clean switch. The frozen blue dot was the warning, not the disaster. Satellites are the reason modern life can agree on where things are, what the weather is becoming, and what time it is.